All right, so today we are going to look at a word problem. We're just going to be using things that we already know, though. So, the word problem doesn't really do much other than set up the situation on how we're going to use our trig function. Usually for these trig functions, they're not just going to expect you to come up with the equation, right? So here, I'll do a little mini physics lesson, but this isn't, I'm not expecting you to memorize this or come up with this on your own. Usually you'll be given a situation with the equation, and then you'll just have to manipulate it. Right. So also, today I will be uploading a list of all of our rules that we learned. I think it cut off at the top there a little bit, maybe. Right, so here we got our Pythagorean identities, we got our cofunction, we have our periods. So actually these show you the period over here. Your reciprocal. Actually, the only thing I'm not seeing is your quotient, which is tangent, is sine over cosine, and things like that. But you got even and odd, product to sum to product, sum and difference, half angles. You will notice, though, and double angles down here. You will notice, though, there are 3 categories that we have not talked about, and that's what we're going to be doing next week. So actually, that's interesting because this stuff allows us to find and use trigonometry to find angles and sides when we don't have right triangles. Right? So everything that we've learned so far about sine, cosine, and tangent stems from a right triangle. Right? That's how we know SOHCAHTOA. That's how we relate the sides. That's how we come up with our proportions. We can use trigonometry outside of right triangles. All right, so that's what we'll be doing next week. All right, so today we're going to look at a projectile motion problem, one of the most basic types of physics problems. And what's interesting about these is we don't necessarily need trigonometry, but trig helps us really dive into projectile motion. It kind of breaks everything down. So just a quick physics. Projectile motion is anything that you launch, right? A football, a baseball, a rocket, anything that gets projected. What's nice about projectile motion? It usually follows the shape of a parabola, more often than not, right? So the squared function. In physics, though, we break things down. So I think I've asked you guys, some of you might be taking physics, some of you might be in other sciences. So this motion here, right, if I throw something and I launch it, right, I give it what's called an initial velocity, right? So I throw it, and as soon as it leaves my hand, that's the initial velocity, okay? There's 2 components to that. There is the vertical component, right? So this would be my velocity. So this would be my velocity in the y direction, and this would be my velocity in the x direction. Right? So the initial velocity is a combination of these 2. And actually, we're going to see something just like this either later next week or in 2 weeks when we talk about something called vectors. Right? So this diagonal motion is made up of a combination of the horizontal motion and the vertical motion, right? So depending on where I'm at, what's interesting is the vertical motion always stays the same, right? It's got the same value. So, if this was 5 miles an hour, this would be 5 miles an hour. This would be 5 miles an hour in the x direction. The y direction is affected by gravity. So when you first throw it, it's got some velocity up there. Then as you move up, it's less because gravity's pulling down. And then at the top, there is no y. And then eventually it starts getting brought down stronger and stronger. All right, and that's what gives it its projectile, this parabolic shape. So we get the x and y directions by setting up a right triangle and just using some trigonometry to find those components. All right, so that's, if you're in physics, that's where we get projectile motion with sine and cosine, and that's what we're dealing with today. So here we have a scenario. A baseball leaves the hand of the first baseman at an angle of theta with the horizontal. So that just tells you that the angle that you're looking at is going to be with the horizontal line, okay, with respect to the horizontal, which is what we usually deal with anyway. And it has an initial velocity, v naught or v0, 80 feet per second. Right, so you throw it, and it's got a speed of 80 feet per second. Player at second base, okay, so some guy over here, which is 100 feet away. This is our initial velocity of 80 feet per second. Catches the ball. We want to find the angle when the range of the projectile is given by this equation. All right, so there's not many things in here, okay? We have the r, the range, the v naught, the initial velocity, and we have our angle theta that it's thrown at. So with these types of problems, okay, I've probably gone over this before, but I like to write down what we know and what we're trying to find out. So we know they tell us the initial velocity is 80, okay, feet per second. Our range, would then be 100 feet. And the angle is what we're trying to calculate for. And so we're just going to plug everything in. So I have 100 equals 1/32 times 80 squared times the sine of 2 theta. So first thing we want to do is we want to simplify. All right, so I'm going to do 80 squared divided by 32. And that gives us a nice 200. Going through our normal algebra steps to solve, we divide by 200, so I get 1/2 equals the sine of 2 theta. Now that I'm here, I could take a few different routes. Okay, we can use our double angle formula, but that would give me a cosine and a sine, right? I know that sine 2 theta is equal to 2 sine times cosine. That's our rule. So if I split it up right now, that would be creating more work for myself, right? I'd have 1/2 equals sine times cosine. And I don't like that because then, I wouldn't be able to split it. It'd be harder to solve. So we're going to do this the old-fashioned way. So I have the sine of 2 theta is 1/2. So again, I'm trying to isolate this theta. So I have to get rid of the sine. So I'm going to write it like this. So to get rid of the sine, we have to take the inverse sine. So if I take the inverse sine of both sides, I end up with sine -1 of 1/2 equals 2 theta. So I wanted to show you this too. You can go ahead and you can find what this is equal to, or you can continue to solve the problem and then worry about plugging it in later. I'm going to do it that way. So again, I want to get theta alone. So in order to do that right now, I would divide both sides by 2. So to have my angle is equal to the inverse sine of 1/2 over 2. So now I want to find what is the inverse sine of 1/2, right? So we go back to the unit circle, or you may have it memorized. All right, so our unit circle, we're looking for the sine is equal to 1/2. So I would have 30 degrees, or I would have 150 degrees. All right, so I'm going to write both of those down. So I either have 30 degrees divided by 2 or 150 degrees divided by 2. Right? Because sine of -1 is 30, or I'm sorry, sine -1 of 1/2 is either 30 or 150. So my angle would either be 15 degrees or what would that be? 75 degrees. So here it's showing you can throw the ball at 2 different angles and you can still get to the same point.
Mr. Murray.
What's up?
So sine, the inverse of sine doesn't really affect the outcome.
What do you mean by that?
So like if it was sine 1/2, and wouldn't it still be 30 degrees? Or does the sine?
Yeah, so what are you saying from this step to this step where I had the sine -1/2 here?
Yeah, I'm saying it would be the same thing as if the -1 wasn't there.
No. That -1 has to be there. So that -1 came there from this step because I have 1/2 equals sine of 2 theta. So remember, I'm isolating this. This is my variable. So I got to do the opposite to this side to remove everything. So the opposite of sine is negative sine. So maybe I should have written it out. So I have 1/2 equals sine of 2 theta. So the mathematical way is I do sine -1 on both sides, like this. And then these two would eliminate each other. And then this you'd have to calculate. So I could have the other thing I could have done, what I was saying is I could have calculated at this step. So sine of 1/2, or the inverse sine of 1/2, we said is 30 degrees or 150 degrees. So then I'd have 30 equals 2 theta, or 150 equals 2 theta, and I'd get theta equals 15 or theta equals 75.
All right, thanks.
Okay, you're welcome. Yeah, so we have the reason we use this inverse sine is because we haven't really done that, or at least we haven't done it in a while like this. Okay, because we want to get that theta alone. All right, any other questions? Good question. All right, so we got 10 minutes. So I'll leave it up to you. You guys can type in the chat, or you can say it out loud. Would you like me to go over any other problems, either simplifying using trig identities, or just solving equations, or anything else?
Can you go over find the exact value problem?
Okay, yeah. Give me 1 second. Let me look for one. So find the exact using like angle addition and angle subtraction.
Either one, because I'm not really sure if I'm doing the double angle right either.
Okay. Let me see. Okay, so let's do a finding and exact, and then we'll do a solve. We'll see if we have enough time. All right, so we want to find the exact value of cosine of 75. All right, so do I still have this? What is this? Oh, I don't need it. Okay. All right, so we want to find the exact value of cosine of 75. Now, we have a few different ways to do this. Well, we're not going to be using product to sum or sum to product. Okay, we're not multiplying two cosines or two sines, or there's no addition there. So when you look at this, there's a few things you want to ask yourself. Is this number the result of dividing okay, before we get to that, remember we have our nice angles, right, that we get from our unit circle. So when we're in degrees, it's a little easier. We have 30, 45, 60, 90, 120, all of these, right? So we're looking for, can I manipulate the angle that I have using any of these combinations, okay? So for the half angle formula, can I set it up? What would an angle be divided by 2 to get me 75? Well, if I had, what's double of 75, right? That's 150. So I can set this up as the cosine of 150 over 2, right? And then I would use my half angle formula here, right? I would plug in 150 for x. So this would be the square root of 1 plus cosine of 150 over 2. And I'd calculate that. Okay, so that's something different that we haven't done. That's something that you can take using a half angle formula. Using a double angle formula. Is 75 a multiple of 2? Well, it's not, so I'm not going to write it as a double angle formula. Okay, if this was, I'm trying to think. I don't think we really use the double angle formula much. No. Okay, so we can also do a combination of either addition or subtraction, okay, using the sum and difference formulas. So 75 is a combination of what? How can I add up or subtract to get 75? So I could do 45 plus 30. I could do 120 minus 45. Okay. I mean, you could do like 60 plus 15, but 15 we don't have. You can do any combination. So actually, let's do, I think we've done the 30 and the 45. So that's one solution. So let's do 120 minus, what did I say? 120 minus 45. All right, so here my u is 120, or my x is 120, and my y is 45. So I'd go here and I'd use this rule. Cosine of x minus y is equal to cosine x cosine y plus sine x sine y. So I'd rewrite this as cosine of 120 times the cosine of 45 plus the sine of 120 sine of 45. Once you get to this part, after you have it split, you would reference the unit circle. Let me get rid of this for now. We don't need that. All right, so the cosine of 120 is negative 1/2. The cosine of 45 is √2/2. Plus the sine of 120 is √3/2. And the sine of 45 is also √2/2. And again, now we're just simplifying. So this would get me negative √2/4 plus √6/4. So I'd combine them. I'm going to rearrange it so I don't have a negative in the front. Negative 6 minus √2/4. I'm sorry, √6 minus √2/4. Now quickly, we got 3 minutes. I'm going to calculate this. All right, so let's see if we end up with something similar. So I have the square root of 1 plus cosine of 150 all over 2. So again, going to this, the cosine of 150 is 1/2. So I get the square root of 1 plus 1/2 over 2. Or 3/2 over 2. Or √3/2. Because we would have 3/2 times 1/2, and we'd have √3/4, and that would give me √3/2. So let's see if they're equal to each other. So √3/2 gets me 0.866. So now I'm going to type in this and see if we get the same thing. So I have √6 minus √2 all divided by 4. Let me close the parentheses. And we don't. Crap, where'd I mess up? Okay, so maybe you don't do it this way. Do it the way that we're used to. All right, so we broke it up. I'll look into this again. And maybe we'll start with that on Monday. Because I just confused myself. That's going to bother me now. Okay, well, I apologize for confusing you and myself. So, yeah, use this method. So, right, we know that 75 is a combination of either 30 plus 45 or 120 minus 45 or any other combination. And then we just use the sum and difference formula. All right, so if you have any concerns or anything about any of the previous stuff, just shoot me an email. And maybe I'll make a separate video that I'll post at some later date where I just go over a few examples. But like I said originally, other than maybe the sum and addition, the sum and difference formulas, we don't see these too often outside of precalculus. So I don't want you to stress yourself too much over them. So yeah. All right, guys, that is our time for today. Have a great weekend, and I'll see everybody on Monday.